dark matter and dark energy. Dark matter, along with dark energy, have become almost universally accepted by science as part of our reality. Today, we are going to try to shed a light on these subjects that don't very often get as much spotlight in the public's narratives. First and foremost, dark matter. What is it? What does it do? What do we know about it? Well, dark matter is a hypothetical form of matter that it is believed to be non-baryonic, that doesn't follow the normal structure of matter of protons, neutrons, and electrons, and instead it is believed to be bound by its own subatomic particle yet to be discovered. Dark matter is invisible, not interacting with radiation or electromagnetic waves as normal baryonic matter does. It doesn't emit or reflect any light. It accounts for 85% of all matter in the universe and a quarter of its energy density, conclusions that were drawn by observing the gravitational effects of galaxies which cannot be explained by normal matter, as it couldn't explain the appearances of some astronomical phenomena. It is believed that it is both common and frequently occurring, playing a key role in the structure and evolution of the universe, with the effects of it most observed in superstructures, such as clusters of galaxies, when they interact with each other or when they spin and don't lose any stars, indicating that the mass of the galaxies is much more bigger than observed. More precisely, 8 times more bigger in order to retain all those stars. If the visible matter was the only matter present, then the galaxy's spin would eject most of the stars. Calculating the mass of the visible matter and comparing it with the results from calculations of the speed and dimensions of galaxies point out that galaxies are much more heavier and denser at their outskirts. Dark matter takes gravitational lensing a step further, not interacting with light directly. Instead, light interacts with the gravity of dark matter, especially along swathes of dark matter, which make it possible to observe the effects and analyze the mass, observing lensing with no obvious source of gravity. These two factors, the spin of galaxies and gravitational lensing out of nowhere, have led scientists to calculate that it outweighs normal matter by a ratio of 5 to 1. At this moment, scientists are searching for a subatomic particle that could be bound to it, giving it its characteristics, that if isolated, will help us better comprehend and understand its behavior and nature. Attempts to recreate it in Large Hadron Colliders have been made, and are being made, along with the help from AI research and simulations. But not much progress has been made so far, and more research needs to be done in order to better understand these phenomena that occur in the universe. Now next, we have dark energy, which unlike dark matter, is an entirely different thing altogether. While dark matter is a physical construct that doesn't interact with baryonic matter or radiation, dark energy instead is an unknown form of energy that is hypothesized to be present in all parts of spacetime across the universe. Sometimes considered a vacuum energy because of its presence in the near vacuum of space, dark energy is theorized to be 2/3 of all the energy in the universe. Although it doesn't have any mass, it vastly outweighs dark matter's share of energy density in the universe of 27%, with dark energy having a total share of 67%, and the rest being baryonic matter and energy at 5%. There are two proposed forms of dark energy: a cosmological constant proposed by Einstein, a constant energy that permeates through space homogeneously, and the scalar fields theory that suggests that there are dynamic amounts of dark energy through all of space that varies depending on its surroundings, which means that it's either everywhere or it varies in quantities depending on its surroundings, like dark matter, with more inclination for the first though. It's estimated to have a very low density, much lower than baryonic matter or dark matter, but nevertheless, it is the prevailing energy in the universe that is present across all of space everywhere, unlike dark matter that varies, representing a negative value in Einstein's cosmological constant that doesn't deteriorate or spread out as the universe expands. Instead, it seems to increase as the universe is expanding. The more space expands, the more dark energy is created, breaking all the laws of normal energy. As such, like dark matter, it was theorized because of mathematical shortcomings. With a negative pressure field in nature, dark energy could be responsible for cosmic inflation, an event that occurred a fraction of a second after the Big Bang, in which a highly repulsive force dramatically and exponentially elongated the universe, flinging out matter quickly and in every direction. It's not clear what links dark energy with cosmic inflation, but the theories of cosmic inflation helped refine those of dark energy. After the universe was no longer thought to contract in the Big Crunch from the gravity of the objects within, and it was discovered that it actually was expanding and in fact accelerating in its expansion, dark energy quickly became the accepted model of explaining this new dynamic. The universe has expanded more in the latter half of its life, creating dark energy everywhere, and because the expansion is everywhere at once, empty space, being elongated at 68 km per second per megaparsec, at vast distances, it's seen to expand faster than the speed of light, half of all its volume being created in the last 5 billion years, out of the 14.8 of its existence. Dark matter permeating spacetime being the catalyst for every point in space that expands. After this realization, the lambda CDM model became the front-running model for dark energy, making Einstein's cosmological model one of the most rigorous and impactful equations regarding this field, as opposed to what he thought after he learned that the universe is expanding, being thought at the moment that it is static, developing the equation with that specific circumstance in mind. The theory of dark energy has been developed by the need for an additional type of energy as a catalyst for the universe's expansion, with many observations around supernovas and cold spots in the CMB to prove its existence, but because of the nature of the energy, observations were unable to be done at a closer range. The nature of it and why it exists is unknown, but it represents a negative value in Einstein's constant. The more space expands, the more energy being created, continuing exponentially. Some theorize that it is a constant property of the universe, but when this was put to the test, results were very inaccurate. One pertinent argument against this was the need for a source outside of spacetime. Another hypothesis arguing that it could be the result of temporary virtual particle pairs that interact with the quantum field following Heisenberg's uncertainty principle. Random pairs of virtual particles appearing all the time and latching on to one another, destroying themselves, creating energy in the process, but the interactions occurs at a very high succession, the energy generated being of an incredible tiny quantity, but over vast distances, adding up, with the counter-argument that the energy generated in this process does not work in the way dark energy does. Nevertheless, a third hypothesis stated that dark energy is just a new type of energy field, but with this theory, its nature, how it's pushing space apart, its form, frequency, and what it comprises are unknown. Also, combinations of all four hypotheses are put forward. Dark energy could be an unknown energy field that permeates all of space as a naturally occurring property of the universe, where the fields work because of the virtual particles releasing energy. Dark energy is all around us, everywhere in the universe, in constant quantities, but because it's so homogeneous and low density, it cannot be detected in a laboratory, not interacting with normal matter, light, or gravity. Some even theorize the dark fluid, with dark matter acting at a galactic scale and dark energy at a universal one. And as I mentioned before, the universe doubled in size in the last 5 billion years. After this point, the proportion of dark energy reached a threshold where it became the dominant energy in the universe, after the decrease in density of dark matter, dark energy being a constant, and since then the universe has been living in the dark energy age. But as the universe expands and objects will only be bound by the gravity of their local structures, everything else will be pushed out of sight, and eventually the heat death of the universe will occur, dispersing all energy, with scientists believing that this will be the end of dark energy, outlasting even the supermassive black holes that we will find at the end of the universe. But in the meantime, more research needs to be done in order to better understand these phenomena and occurrences. Who knows what new technologies can be developed if we manage to better understand what's really happening here. Okay. Thank you for watching the video. I hope you enjoyed it, and until next time, take care.